Hey, welcome to exponential functions. Exponential functions are important functions in the real world in applications, and these belong in topic 2 and a couple of other places in the course. So here we are going to have a look at them in their own right. And an exponential function is one where the variable occurs as the exponent or power. Let's have a look at some graphs here. These over here are typical graphs of exponential functions, and one of these is and one of these isn't. We'll have a look at that in a minute. And here's a couple up here where the base is 3 raised to the variable exponent x, or a third to the x. So these are interesting functions that represent the growth, the rapid growth of quantities, and we're going to study them now. So let's come down and have a look at some of these. And I've taken again some screen clippings from Pearson's textbook there, so you might have that handy by. And in this little exercise here, we're trying to look at the difference between a power function and an exponential function. So you can read what Pearson's has got to say here about that. In a exponential function, you have a constant base raised to a variable power. So they describe that down here. Whereas in a power function, you have a variable base raised to a constant power, something like x squared, x cubed. Whereas an exponential function is 2 to the x or 3 to the x, etc. So they both use the word exponent, which or exponent and power, which often mean the same thing, don't they? That number up the top of a base. But of course it depends on whether x is there at the top, as in exponential functions, or is being raised to the power in a power function. So let's have a quick comparison of these two. Here's x squared and here's 2 to the x. If you substitute x's naught in for each of them, you can see after a while, after this line, you can see that the exponential function 2 to the x, it has a more rapid growth there. Can you see those numbers? For 5, x is 5, 2 to the x is 25, but x squared is 25, but 2 to the x is 32. When x is 6, x squared is 36, but 2 to the 6 is 64. So this is 2 to the x. This is the graph of 2 to the x. This is the graph of x squared. After a while down here, see that point there, when x is 4, they both come to 16. I don't think that's actually the one. Just go back a little bit before here. In there, when x is 4, they're both 16. And then by the time 5, the 2 to the x has started to grow more rapidly than x squared. So, one is a power function, or sometimes called a polynomial function, many powers of the variable, and the other one is an exponential function because the variable is up in the exponent. So much of what we're going to be doing, hopefully, is revision that you've seen before. So let's move down and start looking at the exponential function. Well, first of all, before we draw the graph of that, we have to have a look at some of the rules and properties of power or exponentials. So some of these you've seen before. If you have a base and the base b is greater than naught, and you've got powers m and n, which are rational numbers, ratio of integers like 3 over 2, 2 thirds, 3 quarters, any of those will do. When you multiply two numbers together that are powers of the same base, what's the easy way of working out your answer? You add the powers. Do you remember powers or exponents? Do you remember the proof of that? If you had b times b times b, etc., and so there were m terms here, so it's b to the m, and you multiplied it by b by b by b n times, then there's n terms, how many b's would there be? Well, it would be b by b by b, and it would be adding up the total number of b's would be m plus n terms. So consequently we can say overall that multiplication resulted in b to the m plus n. And you can use a similar proof here for b to the m divided by b to the m. So there'd be m terms there and n terms underneath, and if m was bigger than n, you would cancel them all out, and in the top line you would have m take n terms. So it'd be b to the m take n. If you're considering that m was bigger than n of them would cancel, leaving what's left in the top line, m take n lots of b. And so we go on with each of those. The interesting one here, b to the naught, is 1, because if you have the same number of b's in the top and bottom line, do you remember that they would all cancel as long as b is not equal to naught? And so this would come to 1 on 1, or just 1. But according to our rule, it would be b to the m in the top line minus m in the bottom line. It would be b to the naught. So according to our rules, as we develop our rules, you would have b to the naught. Can we define it in a consistent way? Yes. All the b's would cancel out, and it would be the same as the number 1. And of course, over here then, b to the neg m would be like saying, well, you have a number of b's in the top line, and you have more b's in the bottom line. So using the rule, it would be the number of b's in the top minus the bottom, and if there were more in the bottom, you'd get a negative power, meaning that all the b's that were left were in the bottom. So therefore it's 1 over all the m lots of b would be in the bottom. So that comes as a result of the division rule there for the quotient that you subtract powers. So we are getting some interesting variations, and therefore the rules for exponents, or the definition of exponents, would not just be, we'll just adjust that a little bit here now at the moment, would not just be the number of b's multiplied together, because we need to enlarge the definition. You could have a 0 power or a negative power coming as a result of our developing theory. Alright, so this should be stuff that you've seen before, hopefully, and just making sure now that you know those rules. We'll get to apply them a bit later on. Alright, coming down, of course, there's another type of power that emanates from applying our rules, and that is if you have a base which is positive and you have two numbers m and n that are integers, it's possible to define b to the m over n. Let's see if we can define b to the 1 on n for a start by taking an example, e.g. what would b to the half mean? Well, if you multiply b to the half by b to the half, you just get b to the half plus a half, which is b to the 1. In other words, b to the half is that number multiplied by itself to get b. Isn't that another way of saying the square root of b? What about b to the 1/3 by b to the 1/3 by b to the 1/3? That's b to the 3rd plus a 3rd plus a 3rd, which is b to the 1. In other words, b to the 1/3 is that number which multiplied by itself 3 times here gives back b again. That is the definition, isn't it, of the cube root of b. So can you see, repeating that argument, that b to the 1 on n by b to the 1 on n, if you did it n times, would give you just b. So this b to the 1 on n would be defined as the nth root of b. So in other words, when you have a fractional rational power, the bottom part of that, look at it here, the bottom part in there, the n, means the root. And then you raise b to the m separately from that. So I think the best way of doing these is this one here. Let's do an example. What is the fifth root of 32 squared? Well, we would do the fifth root of 32 and then square it. We'd be saying overall our problem was 32 to the 2 on 5. And we do the fifth root first. And why would we do that? It reduces the size of the number. 2 to the fifth is 32. So the fifth root of 32 is 2. When we square it is 4. So what about something like 8 to the 2/3? Do the bottom part, means the cube root of 8 all squared. The cube root of 8 brings the size of the number down. It's 2, because 2 by 2 by 2 is 8. And now we square it, so the answer again is 4. So the idea of a fractional power, rational power, being the root of a number, the bottom part of that power, the denominator, is the root of the number, is again one of the old rules that we developed in around year 10 level. Let's go on and have a look at, is it possible to raise 2 or any base to any power? We've said x could be integers, m and m in that whole could be member of z, could be positive and negative integers, and m and n can belong to the set of rationals. Any numbers up there we've been playing with are rationals, etc. What about raising 2 to an irrational number? In other words, can we get a continuous 2 to the x function, not just defined for whole numbers or fractions, but can you raise 2 and other bases to an irrational number like pi? Now pi is approximately 3.142, but it keeps going. It's a non-terminating and non-repeating decimal. So you can't write it as an exact ratio of integers. The only exact way of writing it is as pi, that symbol. Let's investigate that. As we raise x to 3, 3.1, 3.14, 3.141, these are all more accurate representations of pi. Can you see we can produce numbers for each of those, and can you see what's happening with these numbers? As we go further and further on, more and more decimal places remain constant. It looks like 2 to the x is actually converging or tending to some fixed number. We don't know what that is because we can't specifically ever terminate pi to 3.141 or 142 or whatever. So, but we can see there is what we call a convergence. 2 to the x seems to be converging or zeroing in on a fixed number. Now, in this course, we're not going to talk about the mathematics of that, but simply coming out of this gives us the idea that 2 to the x or 3 to the x, or in fact b to the x, where we've got b is a positive number, here b is greater than 0, will be defined for all x, even irrational x. things like pi, or 2 to the root 3, or 2 to the root 5 or something. So it means that when we draw the graph will be a continuous. Let's get rid of that now. Hang on, just go back up here. And here it means it will be a continuous function. So in other words, it won't just be defined at whole numbers or even fractions in between, but any possible number can be the power or the exponent of our base 2 or base b. So we will have a continuous curve. We can actually join the dots or the points that we calculate at integral values. And that's something in junior maths, you know, of course. If you join points on a graph plot, it means the graph is defined for all the values in between. So it looks like we have an interesting function here, b to the x, and we can stick any x value in there and we will be able to get an answer. Let's go down and start to look at some of the graphs that will result from that. So the two graphs we're going to try and do now are 3 to the x and a third to the x. So if we look at the table of value here, table of values, what we're looking at is where b is greater than 1 and b is between 0 and 1. So over here we're looking at fractions that we're raising to a power, a fraction, a number less than 1. And let's have a look. If we look at 3 to the x, 3 to the neg 3 is 1 on 3 cubed, because a negative power means 1 over, so it's 1 on 27. Then 3 to the neg 2 is 1 on 3 squared, is a ninth, and so on. 3 to the naught, b to the naught is 1, as long as b is not itself naught. And then 3 to the 1 is 3, and so it starts to grow. So that's the graph over here. So it is defined for negative values of x, because a negative value of x means 1 over the function. The b's, if you like, that are left are in the bottom line, and then we have the positive values over here. Can we join them? Yes, we can join the points. Join the points because we have discussed in an informal way that this function will be defined for all x. Join the points because 3 to the x is defined for all x, not just for whole numbers, not just for fractions, but for irrationals, everything in between. What about a third to the x? Well, a third to the neg 3, we better look at that. Third to the neg 3. First of all, the negative means the reciprocal, so this becomes equal to 3 to the 3. The negative power means 1 over a third, which is 3 to the 3, which is 27. And then a third to the neg 2. Negative power means 1 over, so that's equal to 3 to the 2, or 9. And so we go, and a third to the naught, b to the naught is 1, as long as b is not itself naught. A third to the 1 is just a third. A third squared is a ninth, and a third cubed is a 27. So the interesting thing here, for a third to the x, for negative x values, it starts off large up here, and then as x goes positive, it decreases. So one function is called an increasing function. So this is the one here. As x increases, then 3 to the x increases. But over here, as x increases, the function decreases. It's called a decreasing function. And what do you notice about them? Well, it looks very much like they are reflections in the what? Y-axis. Reflections of each other in the y-axis. can we check that algebraically? Well, let's take 3 to the x, and if we were going to reflect it in the y-axis, remember its image function becomes f of x equals, or we might call it, let's call it g of x, because it's the image function. G of x equals, what do you do to x if you're reflecting it in the y-axis? It becomes neg x. Do you remember that from transformations? So 3 to the neg x, that's 3 to the neg 1 all to the x. 3 to the neg 1 is a third to the x. So we can actually prove algebraically down here, using our transformation geometry, that reflecting 3 to the x in the y-axis, replacing the x value by neg x, does produce a function a third to the x. So this transformation association is very important in empowering you to understand a whole range of functions that are connected by some fairly basic transformations. Alright, so keep thinking about those things. Let's come down now and make a summary of what we've found. So exponential functions, we're talking about a base number which is greater than 0 and not equal to 1, because 1 to any power would just be 1. So we're calling the exponential function some function which has a fixed base and the variable is in the power there, or exponent. What is the domain? What values can you put in? Any x value. Because we see they're either like that, an increasing function, or like this, a decreasing function. This is when b is a number bigger than 1, and this is when b is a fraction. Raising a fraction to a higher and higher power here causes a decreasing function. We just did a third to the x. Raising a number bigger than 1 to a bigger and bigger power is an increasing function. So we get the range, so you can see here, looking along the x-axis, x is a member of R for both of them. But looking at the range, let's go up and down, we can see that as x takes large positive values, one of them tends to 0, and the other one, as x takes large negative values, also tends to 0. Okay, so this is the one on the right there, the decreasing function. This is the one on the left, the increasing function. But both of them, if you're looking up and down in y-land, they both don't exist under the x-axis or under y is equal to 0. So the range, going back up here now, the range is y is greater than 0. And we call y equals 0, or the x-axis, a horizontal asymptote, because it's a line that the graph approaches. That's what an asymptote means, but actually never crosses in that range. Either x is tending to positive infinity or x is tending negative infinity. It's approaching it but doesn't ever meet it. So over here, one is called an exponential growth curve, and the other is called an exponential decay curve. One is growing and growing in value, and the other one is decreasing or decaying in value. So they're our basic functions, and I think you would have in general seen an introduction to that, at least in your work up to year 10. Let's go on then and have a look at, if we understand those functions, what about trying to transform them or move them around, move the points on the plane. But what we're going to do now is to take 2 to the x and have a look at what happens when we do some of these basic transformations that we looked at before, where we have 2 to the x and we might change the x term, multiply the whole function by value, and so on. So let's have a look at the first one. And what's the connection between 2 to the x plus 3 and 2 to the x? Well, if you remember from before, what have we done? There's our parent function. We've added 3. So that means we have translated the function 3 units in the y direction. So let's do it. Here's 2 to the x, and every point has been moved up 3 units in the y direction. Say y translation. So what would the new domain be? Well, we've only moved it in the y direction. We haven't affected the values that we can use in the function. So x is a member of R, and now the range is y is greater than 3, because we have moved it up 3. So 3 is the asymptote now, whereas y equals 0 was the original asymptote. Now y equals 3 is the new asymptote, or line that the graph approaches, because each point on the plane has been moved up. Here it is back up here, remember this, 3 units. The y value for all points has had 3 added to it, a y translation. This transformation work from before is extremely important in understanding a range of functions. Let's look at the next one. So here's the graph of h of x equals 2 to the neg x. What have we done? We've changed the x term by multiplying by neg 1 and making it neg x. Do you remember that when you do that, you actually reflect the graph of f of x. They made a mistake here. Across the x-axis. That's not right, is it? It's across the y-axis when we change the power term. So 2 to the x, the graph is right, has become 2 to the neg x. And of course we know that this is correct because 2 to the neg 1 all to the x is 1 on 2 to the x, or a half to the x, which is a decreasing function. So this is actually a reflection across the y-axis, and the domain will still be x as a member of R. We're not actually changing behaviour this way. That's the domain. We are not actually changing the motion this way, which is the range, because we're not moving it, we're simply reflecting it across the y-axis as if it's a mirror. So that point travels to there, that point travels there, etc. So the range is still the same. Range is y is greater than 0. And the horizontal asymptote is also still the same under this reflection. All right. Let's try to recall some of this stuff in transformations. Moving on. Excuse me. Moving on now, we've got a graph of p of x equals neg 2 to the x. We're multiplying the function by a negative here. And now this time they've got it right. It's reflection across the x-axis. That is correct. When you multiply the whole function there, down the bottom here, by negative, these positive values go to 2, 4 becomes 2 neg 4. 1, 2 becomes 1 neg 2. They all go from above to below. So have we changed it in the domain, the set of x values? No. Domain is still x is a member of R. The range is a bit different now because we have reflected it here across the x-axis. So here the range is now y is less than 0. Just watch that. It was y greater than 0. Horizontal asymptote, still the same. The x-axis, because we're only reflecting across it. All right, we've got to think hard about all that earlier work on transformation geometry. Let's move to the next one. So in this one, 2 to the x take 4. Let's just come down here and just have a look at that one. So what have we done here? Well, instead of the x term, we've put x take 4. So that means we're translating it 4 units in the x direction. Remember, it's the opposite sign to that constant, is the direction of the movement. So here, 2 to the x has been moved across 4 units. 3/8 becomes 7/8, and so on. Will that affect the domain, the set of values we can have across here? No, it'll be x as a member of R. And will it affect the range? Well, no, it's moving across, it's not moving up and down, so the range will not be affected. It will be y is greater than 0, and the horizontal asymptote will stay the same. And we're just moving it in the x direction. Let's have a look then at part E, where we've got 2 to the x, there's our parent function in there, and we've multiplied it by 3. Do you remember? That's a vertical stretch by a scale factor of 3. So it's going to be stretched in this direction. Every early y value is going to be multiplied by 3. So here, what's the domain? Has it affected anything this way? No, the domain is x as a member of R. And the range, it's only stretching. So it will still start at y is greater than, or well, it won't start there, y equals 0 is the x-axis asymptote, but it will only exist above that. So the range is y is greater than 0, and the asymptote is y equals 0. Alright, so that's a good bunch to think of. Let's go down and see some exercises now. I want you to have a go at each of these. And the idea, of course, is to use your idea of transformation geometry to draw a graph of these and then state the domain and range. And it's important to do this as a paper 1 question, that is with no calculator. So I want you to use your transformation geometry ideas and no graphics display calculator to get a graph and to state the domain and range. And then there's a general thing here. So that's talking about a general function with some C's and D's and A's in it. What do they do? And then the idea here is to, in part 5, is to have a look at each of these different functions and try to explain why they behave like they do. So on the Casio, I don't know whether you want to use dynamic mode. You can actually enter the function y equals a to the x and then set a up as another variable going from 1 to 8. And you can see dynamically the graphs flashing there, 2 to the x, the same point there, 3 to the x, 4 to the x, and so on. Hard to draw them just like that, and it will go up and back dynamically. Just noticing there, do you realise that where it cuts the y-axis, where a graph cuts the y-axis, always x equals 0, and 2 to the 0 equals 3 to the 0 equals 4 to the 0, etc. Any base raised to 0 power is 1. Then it comes to 1, so they all go through the point x is 0, y is 1. That's an interesting observation. Okay, now here the last couple of questions are general questions. I'll leave you with those as a general revision of trying to get familiar with these exponential growth and decay functions. And in the second part now, 4.2, we're going to actually look at using these functions to model various behaviours in real life. So have a look at those down here. Now are the solutions, there's 1 and 2. When you've had a go, come down and pause it and mark your work. Then there's actually 3 and 4. Okay, you can pause that. 5 and 6 and 7 or 5, that's the first part. And I've left it with the TI format there. You can do the same thing on the Casio, slightly different entries. So there's 5, rest of 5, and then just coming up here, 6 and 7. So go back and have a look at the problems. Back up here, and then just toggle back and freeze it, and have a look at whether you got the graphs reasonably correct there. Okay. Be particular fussy with the x-intercept, so just reiterate, the y-intercept, sorry, just reiterating. You might try putting a few points in and getting a reasonable graph for those. Alright, so there are going to be several presentations based on exponential functions. It is a very important function in this course, or they are a group of important functions, and logarithmic functions, and the connection between the two is important as well. So at the moment it's cheers from me, but I look forward to seeing you in the next presentation. Keep building those skills. Cheers for now.